we're going to see there's special significance to this n, and it should look familiar. Maybe you recognize that as principal quantum number n. Principal quantum number. Okay. I'm going to come back full cycle around this. This is exactly the n that you are thinking of back to your general chemistry days, right? For 1s, 2s, etc. And we're going to connect how that has established itself as this principal quantum number, okay? It's a solution to the Schrodinger equation. So now we have to normalize this wave function for that C constant, okay? And so let's do it. So recall, and we also want to normalize this specifically to our boundary condition, all right? So I'm going to establish this normalization constant over the range 0 to L, right, as given by the length of my box, okay? And that's going to be the square modulus dx. And then I'm just going to keep using the same letter just to not confuse it. So we know that that's going to be c squared in front, and that all equals 1, all right? So now plugging all of this in, I'm going to have c squared times the integral from 0 to L. And we can just make this sine squared, okay, square modulus. So that's going to be sine squared of n pi x divided by L dx, all right, all equal to 1. And as it turns out, that has a standard solution. So the integral from 0 to L of sine squared n pi x over L is a very easy solution. So all of that is just equal to L divided by 2, that whole integral, all right? So then there's still times a sine squared equals to 1. And so now rearranging this here for C, right, this becomes, so multiply 2 over L, take the square root. This becomes the square root of 2 divided by L. And so now I'm going to write this new wave function here as psi. And I'm going to write here a capital N to tell me that it's been normalized. But I'm also going to put this lowercase n to tell me that I've got this new wave function that's dependent on this interesting integer, this quantum number n. Okay, so now 2 divided by L square root of sine n pi x over L, and this is my wave function for, so my normalized wave function for a particle in a one-dimensional box. And then of course, so this is only over the range 0 through L, right? Because outside of the box, the particle can't exist, okay? So what do we get from all this if we keep going? So we established this kind of funky n, right? So what I also want to show you, very quickly, if I back up here and I look at the eigenvalues, okay? So we also know from this solution that E equals k squared divided by, or k squared times h squared divided by 2m, where k equals this 2me divided by h squared, okay? Well, we also established from this that k equals, where did it go? I lost it. That k equals n pi over L, okay? So if we combine those two things, so k equals n pi over L, but it also equals 2me over, and I'm going to write this as, instead of h bar squared, I'm going to write this as h squared over, so that would be 2 pi squared, which would be 4 pi squared. And we know that's all square root. Okay, I'm going to do some algebra and rearrange and solve for E here. And I'm just going to show you that solution on the next slide, okay, that we have right here, okay? So once again, where did that come from? So that came from the fact that we know k equals 2me over h bar squared square root. But we also know that that equals n, what did we say? That it's n pi over L. All right. So instead of writing here h bar squared, remember h bar equals h over 2 pi. I'm just using h here because that way we can cancel the 2 pi's, right? There's a pi on this side of the equation, and there's a pi buried in that Planck's constant, okay? Those all cancel. And now what we get is energy as a function of this number n goes as n squared h squared divided by 8ml squared for the normalized wave function that we just came up with between 0, x, and L, okay? And so you'll notice that I've got a couple pictures going on. Here I've got this picture right here, but I've also got this graph, right? That's going to be your Mathematica 3 assignment. And I want to show you through this manipulate function what's going on when I change this value of n. And so for now here, I'm just looking at a box that has length of 2 pi, okay? So, and then you can see the same established graph right here for this case where this is 1. So that's n, the values of n right here, okay? And so now as you can see, when I add another value of n, oh, of course it didn't update for me. So let's evaluate this notebook here. Okay, great. So now when I go and add values of n, so I make n equal to 2. Look at that. I get another period there. And now when I add n is equal to 3, I'm getting another one, and another, and another, and another, and another. Okay, so I'm getting these integer values. Okay. We will see in the coming slides that this E as a function of n, these are very much related to the energy levels of particles or the particle in the box. Okay. So we established here that the only energy that we have in this box is kinetic, because V is equal to 0, okay? But so this is the solution to the kinetic energy, k squared h bar squared divided by 2m, all right? So it's that same energy. We know that's its only energy, which is kinetic. So what we're seeing, what's really cool about this is that kinetic energy does not have continuous values, rather it has quantized values. So in other words, when n is equal to 1, we know it has the value of h squared divided by 8ml squared. However, when n is equal to 2, it goes up by the square. So now that n is equal to 2, right, becomes 4 times h squared divided by 8ml squared. When n is equal to 3, it goes up by the square again. It goes up to 3 squared is 9 times h squared divided by 8ml squared, okay? So we're going to see some pretty cool implication from this. And so we establish here that these n values make up different quantum states. And the reason why they make up different quantum states is because they're a different eigenvalue. Each time we change the number n, we get a new eigenvalue. So in other words, psi of 1, plugging into this function, right? Psi of 1, square root of 2 divided by L times sine of pi xl, that describes one state. But when n is equal to 2, okay, that's now going to be sine 2 pi x divided by L. That's going to be a new state. And these states are quantized by this level n.